Welcome all to this new appointment with the Astrophysics Vergata seminar series. Today we have the pleasure to have with us Dr. Eleonora, who in my opinion represents one of the most beautiful and concrete examples of what women can achieve in science. She started her career in Italy at the University of Palermo, and then after a PhD, she moved to United States, where she worked at the NASA Goddard Space Flight Center and at the University of Maryland. She has been awarded many prizes, the latest of which being the NASA Silver Achievement Medal and the ERC Consolidator Grant with her Bianca project. Hopefully, by the end of the year, she will be joining us here in Rome. And today, she's going to talk to us about neutron-star collisions, which is one of her main research topics, including gamma-ray bursts and kilonovae and tidal disruption events and gravitational wave sources. So, Eleonora, the floor is all yours. Go ahead.
Thank you so much. Thank you for this very flattering introduction, for inviting me today. So let's start. I will introduce you to the focus of my research and also the focus of my ERC Consolidator Grant, which I hope to carry out in the next 5 years in Rome, Italy. So we will talk about what happens when two neutron stars collide. So I will start with a brief introduction about neutron stars for people who are not familiar. So what you see here in this beautiful, colorful image is the remnant of a supernova explosion that happened about 300 years ago. So you see all these colorful layers. These are the layers of the star ejected away during the explosion. But I would like you to focus your attention on this little dot at the center of the remnant. What you see here is a neutron star. So we know that these very special stars form at the end of the life of very massive stars. And the reason we are so interested in them is because they are some of the most exotic objects in our universe. And to explain you why, I try to compare in this map, I try to compare a neutron star with the city of Rome. And you will see that the neutron star is a star that is even more massive than our sun, but it's as big as the city of Rome. So you can imagine that something really extreme happens in these conditions. And indeed, these are some of the densest and hottest stars known in the universe. And the reason we're so interested in them is because we can probe the law of physics and gravity in these extreme conditions that cannot be reproduced anywhere on Earth or even in the universe. They're very rare conditions. In my specific studies, I'm interested in a very rare form of neutron stars, and these are neutron stars that come in pairs. So not isolated neutron stars, but binary neutron stars. And we know that this type of binary systems exist. They were discovered in the, I think in the late 60s, early 70s. This is an example of the first and most famous binary neutron star. This is known as the Hulse and Taylor binary. And you see these two dots are these two neutron stars, and they kind of dance around each other along this path that in astrophysics we call orbit. And the discovery of this very special system actually was so significant that it led to the Nobel Prize in 1993. And the reason this is so significant is because it really allowed us to test gravity, and it provided us the first indirect evidence of what we call gravitational waves. And you can see the importance in this very simple diagram that shows the distance of the two neutron stars as a function of time. So you see, okay, here the discovery is early 70s, and you see how the distance between these two objects slowly decreased with time. And you know, if there was no general relativity, if there was no gravitational wave, the distance between these two objects is supposed to remain constant. But because general relativity, it follows this parabolic decay. And you see how the data points perfectly match the prediction of general relativity. So this was the first indirect evidence that Einstein's theory was actually working. And most recently, we got the direct detection of these gravitational waves. So you see here an artistic rendition of what gravitational waves are, but it's quite accurate in the sense that they can be described as a warpage, a distortion in the fabric of space-time that is caused by the movement and the acceleration of masses. However, the problem that we have is that these ripples in the fabric of space-times are exaggerated here in this image because in reality they are extremely tiny. So in order to detect such tiny distortion, we needed 4 decades of work by the LIGO and Virgo collaboration and a leap in technology. And also we can only detect these for very special systems like 2 neutron stars moving around each other. And the reason we need these systems and the reason they're so important is because any other type of mass will produce a signal that is too small to be detected by our instrumentations. So we need very massive and very dense objects such as neutron stars and black holes in order to detect these gravitational waves. And indeed they were directly detected in 2015 for the first time. And this led to another Nobel Prize in 2017. So as I said, the first detection of gravitational waves was in 2015, and it was made by the collision of 2 stellar mass black holes. In 2017, we had another breakthrough, and this will be the focus of this talk. So this is these are the breakthrough observations that really changed my field of research, and I think the whole field of astronomy. What you see in the upper panel is these are the observations by the gravitational wave interferometers. And what you see here, this curve, this green curve is actually the signal. So the most colorful, the most intense is the color, the strongest is the signal. And you see that it kind of changes in frequency and becomes stronger until it disappears. And this is the time in which the 2 neutron stars actually collided. So because of the properties of the signal, which was extremely long in duration, so it had a very distinct properties from collision of black holes. So the LIGO and Virgo team were able to identify that this collision was made by 2 neutron stars and not by 2 black holes. And what was really surprising that after these observations were performed, just 1.7 seconds later, our satellites in space detected a significant increase of gamma ray light coming from the same location in the sky. And you see that in the bottom panel. What you see here is the gamma ray light recorded by the Fermi Observatory. And you see that after a couple of seconds, since the merger, there is this spike in the gamma ray light. And thanks to the contribution of many instruments, including Integral, which is a European telescope, and clearly Fermi, this gamma ray light was localized at the same location of the gravitational wave signal. And this very simple measurement allowed us to test a 100-year-old prediction, that is that gravitational waves and light move at the same speed. And we clearly knew that because we knew that these two signals were born from the same object, and they were traveling very far. We knew they were coming from hundreds of millions light years from us. And so since they started more or less at the same time and they arrived more or less at the same time, we can say that the speed of gravity and the speed of light are mostly consistent. And so here, thanks to the work of astronomers, we were able to actually localize with great accuracy these collisions of neutron stars. And what you see, this is a beautiful image collected by the Hubble Space Telescope. And this is the home of the gravitational wave transient. The name in astrophysical language is called NGC 4993. And you can see it has this very oval shape with not a lot of structure. So we think this is a kind of an old galaxy hosting a lot of evolved stars, such as neutron stars. So it's a typical home for a system of two neutron stars. And thanks to this localization, we were actually able to measure the distance. So we knew that this event happened 130 million light years from us. So in astronomical units, that's more or less 40 megaparsec. And so you see this little orangey dot was the optical and infrared counterpart of the gravitational wave signal. So in addition to the gamma ray light, we discovered that there was something else in the optical and infrared. And so this signal is called kilonova. And you see here its evolution as a function of time. You see initially it was very bright and also very hot, with an estimated temperature of 10,000 Kelvin. And then you see how it rapidly changed, not only in brightness. So it really dropped within a few days. It dropped by 2 orders of magnitude in brightness, but also in color. You see that initially it was very hot and blue, and then as soon as the brightness decreased, also the color changed toward redder wavelengths. And this means that it was cooling down and toward temperatures around 3000 Kelvin. So this transient was indeed long postulated to exist after the collision of two neutron stars, but it was never clearly found until 2017. So this was really the very first and unambiguous confirmation that this fast evolving and red transient named kilonova exist, and they follow neutron star mergers. And the reason we're so interested into this kilonova is because of their origin. We think that the way this signal is produced is when heavy elements are actually forged in the aftermath of the neutron star collision. And so to make you understand what happened, you have to remind that neutron stars are actually very exotic systems, and definitely, as you might understand, they're very neutron rich. So when the two stars collide, all this neutron-rich material which is also very hot, is ejected into the outer space. And these are the conditions that are very unique in space to trigger a nucleosynthesis process that we call rapid neutron capture, or more commonly our process. And here, this is a little cartoon trying to explain how the ARP process works. So what happens is that in the medium surrounding the collisions, there are these there are these seed nuclei, and they get bombarded with all this neutron-rich material. And because of these bombardments happens in such a special setting, so it happens very rapidly at very high temperatures. And so these nuclei simply accrete neutrons, and they don't have the time to decay. So what happens is that the initial nuclei gets heavier and heavier and heavier until the neutron flux stops. And then at that point, these unstable nuclei can decay into stable isotopes. And so this radioactive energy that is released in this process is the energy that powers the kilonova. And this explains why we're so interested in studying this type of explosions, because the light of the kilonova might carry the fingerprints of the elements created in the merger ejecta. And here is an example that I show. This is what we call spectra, which means this is the basically the brightness of the kilonova light as a function of its energy or wavelength. And you can see that this dotted line shows the standard black body spectrum that we expect to describe the thermal emission of a kilonova. But you can see that the observed light is not perfectly consistent with this featureless black body spectrum. So there are valleys and hills that start to appear in the spectrum. The more we observe, the more we see these features changing. And this is very important because these are the signatures of the elements that were freshly produced in this neutron star collision. And so by identifying these, the elements producing these features, we can actually test the composition and the chemical abundance of these ejecta. And so why this is important is because this may allow us to answer one of the most ancient questions posed by the humankind, which is what is the origin of gold and all the heavy metals. So here is you see how in human history, this shiny metal, gold, always fascinated the humankind. And for example, in the Roman era, it was commonly called as the metal of gods. And even in the Aztec religion, for example, kind of went close to its true origin. So gold was considered like sweat of the sun that could be collected. So these drops of sun could be collected on Earth, and therefore they had immense spiritual power. Being less religious and more scientific, the origin of heavy elements has been a very long-standing issue in modern astrophysics. That started with this with this seminal review in 1957 by Margaret Burbidge and collaborators, where they review how all the elements that we find on our planet are actually created in stars. And indeed, they point out that the observational evidence for the production of our process heavy metals was missing. And in this review, they actually suggested it could be found in spectra of the supernovae. But this observation of 2017 proved that, at least in some cases, it's going to be found in the collision of two neutron stars. And so this is this was a landmark observational discovery that really addressed this 60 years old mystery. But the reason I say it, at least in some cases, is because this mystery is really not fully solved. So with one single observation, we still have many questions to answer. And the reason is that we have very strong observational constraints coming from our solar neighborhood about the abundances of heavy metals. And what you see in this plot is the typical abundance measured in the solar neighborhood, which is also consistent with the abundances measured in metal-poor stars. So it seems like there is a robust pattern of our process production in our galaxy. And in order for us to say that neutron star collisions are the origin of all the heavy metals, we really need to match the observed pattern with the pattern derived by our observations of colliding neutron stars. And otherwise, you know, there might be another source. So, the reason I say that, because not all the kilonova can produce the whole spectrum of heavy elements that we see in our solar system. For example, there are some kilonova that we call blue kilonova because they're really hot and they emit most of their light in the optical. These blue kilonova actually can produce light, our process elements, but they have a lot of troubles forging the heaviest elements. And an example, here you find 3 cases of kilonova candidate that we found associated with gamma ray burst. And all of these tend to be blue. So partly because of you know, the limited sensitivity of our instruments at red wavelengths, we could not really find any other evidence for the formation of heavy elements in kilonova beside the one discovered in 2017. So this whether you know, this red kilonova emission is a common feature and is found in all the neutron star collisions or all in some of them, this is really open questions in the field that we hope to address in future years. And indeed, we hope that the forthcoming James Webb Telescope, which, as you know, is very sensitive at infrared wavelengths, may help us understand and solve this problem. And here you see some predictions. So you see that these are 3 different curves that describe the luminosity of the kilonova as a function of time. And you see that at early time, when the kilonova is really bright, so everybody is good at observing it. But at early times, all these predictions kind of fall in the same region. So it's going to be very hard with our observation to distinguish between models. But at very late times, when James Webb is needed, because we need the right sensitivity in the infrared, at very late times, these models actually deviate from each other. And you see, this is the model of a blue kilonova, so with very light R process elements. And this in red is the model of a red kilonova producing a lot of heavy elements. And so by performing these very simple observations, we might in the future be able to probe the nucleosynthetic yields of kilonova in much greater detail. And so now I'm gonna talk about another component of neutron star merger. So this was clearly the shiny argument about the origin of gold and the kilonova. But what you see in this cartoon is a representation of what happens when two neutron stars collide. So you see that there is this, at the center, there is the remnant of the collision, maybe a black hole. And then there is this cloud of neutron-rich ejecta that produce the kilonova. But there is another very important component that is this very fast outflow moving at a speed close to the speed of light. And this very fast outflow produces the gamma ray burst that we saw at the beginning, but produce also another signal that we call afterglow. So what you see here is the X-ray afterglow of 170817. So at the center, this is a beautiful image, very deep image taken by the Chandra X-ray Observatory. And this is the field where the explosion, where the collision happened. So this is the center of the galaxy, this bright dot. And here, right up left, you see the X-ray remnant of this collision. And these little stamps that you see show you the temporal evolution of the X-ray emission. And as you see at the very beginning, when the kilonova was really bright and everybody was excited by it, there was no X-ray emission. And it was a big surprise when 9 days later, my team and I found this weak but very significant source arising in flux. And you see that this rising flux continued for several months. It became 5 times brighter 100 days after the merger. It peaked at 160 days after the merger, and then it rapidly fell down. But I can tell you it's still visible. So the last stamp that you see here, these are observations performed between December 2020 and January 2021, so just 2-3 months ago. And you can see that a weak source can still be detected with the Chandra X-ray Observatory. So there is still a lot to learn for us. And here is the spectrum of this afterglow. So again, you can see these are the X-ray wavelength, optical, and radio. And what we found that basically the entire spectrum from radio to X-ray, so we're talking about 10 decades in energy, the entire spectrum can be described by a very simple power law. So, and this is quite unusual for gamma ray burst. We don't quite understand whether this is a feature of this event or is going to be the same for all the gravitational wave counterparts. But it was very useful for us to derive the properties of the jet, of this ultra-fast outflow creating this afterglow emission. So for example, we could understand that this afterglow is powered by synchrotron emission from a population of accelerated electrons. And we can actually measure, because of this very constant power law shape, we can actually measure the spectral shape of these electrons with a great accuracy. But we can also probe the medium surrounding the collision thanks to these afterglow observations, and we derived that the explosion happened in a very low density environment, which we kind of expect in a galaxy similar to the NGC 4993. So it's a very old galaxy, not a lot of star formation and clouds there. So here there are some key observations that were made to show that the properties of these X-ray transients were consistent with collimated outflow, we call it jet, that was moving at a velocity close to the speed of light, but not only that, it was tilted with respect to our line of sight. And this was proved very nicely with high resolution radio imaging of the source. You see here the VLPA image that shows the centroid of the radio emission. This was taken, I think, 100 days after the merger, and this was about 250 days after the merger. And you see that the movement of the centroid actually implies that the source was moving with a velocity 4 times the speed of light. And we know that this is a typical, we know this from AGN studies, we know that this is the typical signature of a relativistic jet that is seen at an angle. So it looks like that the distance traveled by the light is this small, but in reality, you know, this is what we observe, this separation, but the distance traveled by light is actually much larger. And this is just a geometrical effect due to the specific geometry of the system. So here is again how viewing angle changed our way to study the afterglow of these neutron star mergers. Is because the viewing angle actually changes the shape of the afterglow quite drastically. And here is an example. So the short gamma ray bars that we observe routinely with our telescopes are usually very far from us. And therefore, we can only see them only if our line of sight is perfectly aligned with their outflow. And this is how their afterglow looks like. So you see, it's very bright at the beginning, and then it rapidly fades away. The GW170817 event was instead seen because it was very close to us, but its outflow was pointing in a different direction. We think about 25 degrees from us. And you see how it looks completely different. So it started really faint. Then it started to increase in brightness. It peaked several months after the merger, and then it decayed very rapidly. And so we think that, you know, even if the explosion properties of a neutron star collision are the same, we are gonna see a variety of behaviors in their counterparts just because their system is so anisotropic. And so the viewing angle are going to shape the observable properties of the explosions quite drastically. And you see here another example of an intermediate case that we discovered in 2018, sorry. So this is again is a GRB, and this GRB had this very odd afterglow shape that we could not comprehend very well until we saw the gravitational wave counterpart, and then it became clear that this was an intermediate case of gamma ray burst that was seen at an angle that was slightly closer to our line of sight. So this was 25 degrees, so this GRB was about 13 degrees, and this is how the afterglow looks when it's 0 degrees. So we are gonna have this full spectrum of behaviors that are waiting for us. But, you know, one advantage of this dependence of the emission on the viewing angle is that the electromagnetic radiation can help us to constrain the properties of the emitting source, because the electromagnetic radiation can constrain the distance scale of the emission through the measurement of the redshift, but the afterglow studies can also constrain the inclination of the binary, which is very likely aligned with the jet of the emission. And so you see here an example of how the combination of gravitational waves and light may help us you know, test a new way to measure the cosmological parameters. You see here this broad shape is the constraint on the cosmological constant, the Hubble constant, made with gravitational wave and redshift measurement. And you see how the addition of afterglow studies clearly narrows down the shape just with one event. So the prospect is that if in the future we will be able to collect more of these events, then we might achieve the precision of other measurements like the one made to supernovae type 1a or the cosmic wave background. And so this opens up the possibility to use neutron star mergers as probes of the expansion of the universe. Now, what I would like to, conclude this talk is to give you some, to outline some of the possibilities that are lying ahead of us. So things that we did not discover yet, but actually are within reach of our future observations. So what you see here is a summary of the results of the LIGO and Virgo observations since 2015. So you see there is an entire new population of objects that we were not able to discover through light alone. And in particular, my research focuses on this area. You see, this is the least populated area at the transition between a neutron star and black holes. And so we expect in the next few years to be able to populate this area and really find a new type of transients, thanks to the indication of gravitational wave astronomy. An example is what we call the choked jets. So I showed to you that the binary neutron star merger discovered in 2017 was actually powered by this collimated, very fast outflow moving close to the speed of light. And this is the standard model that we associate to neutron star mergers. But actually, many simulations of neutron star mergers fail in reproducing this jet. And so we think that in other cases, because of the large cloud of kilonova ejecta that is surrounding this poor jet, the jet is going to be choked by them. So it's not going to be able to accelerate to this very ultra-relativistic velocity, but it's going to be choked. This is not only a new type of transient that is going to give us completely new signatures in the electromagnetic domain, but it's also thought to be probably our best chance to detect neutrino in conjunction with neutron star mergers. And so it's a very exciting perspective that we might be able to discover in the future. Clearly, another, if I have to compile my wish list, another event that we all are waiting to see is the collision of a neutron star and a black hole. Because in theory, they could be similar to neutron star interactions, but we don't know exactly. We don't know if they're going to produce any form of light or not. So definitely this is going to be a very exciting discovery. And indeed, even in the last run, we started to probe this parameter space. We didn't find any electromagnetic light, but here I show the observations that were performed for this transient called 1908-14 BW, which is, we don't know exactly, but it could be a neutron star black hole collision is one of the possibilities. And you see this is the localization of the gravitational wave signal, and this localization was very accurate, so it allowed us to completely cover this region with our optical and radio telescopes. And these are a few candidates that we found. We thought that they were possible counterparts, but then thanks to the very detailed observations, we were able to rule them out. So in this case, we didn't find it, but we're definitely probing that parameter space. And we expect it to continue to improve in the next run that will start in 2022. And the last discovery that is actually happening right now is the possible discovery of a kilonova afterglow. So what you see here again is the X-ray, the evolution of the X-ray emission from 1708 to 17. So these all part from 9 days until 3 years. Is very likely powered by the ultrafast outflow that we call the relativistic jet. But in the last few months, we saw that the X-ray emission actually stopped its decay, and it's now kind of flattening. And so this is who knows what is going to be, but one very exciting possibilities is that the X-ray emission is going to brighten up again. And this new component is produced by the kilonova ejecta, so the same ejecta, the same material that created the optical and infrared emission at the very beginning of the story, 3 years later is actually catching up and is interacting with the surrounding medium, and it may create a sort of X-ray and radio remnant. And if that happens, then the emission is supposed to rebrighten and be visible for several years to come. So we're definitely testing this right now. I'm actually writing a paper this week. So why this is important? It's important because it gives us a fresh new look into the ejecta of this merger, a look that we cannot probe with the optical and infrared observation of a kilonova. When we observe a kilonova, we actually probe the mass-weighted ejecta. We just probe the behavior of the mass, the majority of the mass of this ejecta. But we know that there is a velocity stratification in this ejecta. So most mass is here, and it's moving at a speed that is like 20% the speed of light. But you can see that there is a little bit of mass that is accelerated to much larger velocities. And this distribution of mass is completely missed by the optical and infrared observations. We just cannot see it. But it's very important, because you see that these are simulations carried out for two different behaviors of the neutron stars, what we call equation of state. And you see that two different equation of states can give two very different behaviors. In particular, we think that if the equation of state is very stiff and we can support the formation of a hypermassive neutron star rather than a black hole, then this might accelerate the ejecta to this very large velocity close to the speed of light. So being able to detect the evidence for this very fast ejecta will give a very important indication about the properties of the neutron star at the moment of the merger. So this can be done only with these late time X-ray and radio observations that we are carrying out right now. So I will conclude with the summary that these systems, these pairs of neutron stars are actually unique astrophysical laboratories. And I hope that in this talk I managed to give you a glimpse into the realm of problems that we can address by studying these systems. They're really touching several fundamental issues, from test of gravity and cold ultra-dense matter to cosmology to nuclear astrophysics, the formation of cosmic heavy metals, and clearly the formations of these relativistic jets that is very important in high energy astrophysics. So all these topics, will be the focus of my ERC grant that I hope to start in the next few months in Rome, actually at Tor Vergata University. And the main idea will be to start from this initial phase of discovery that we saw with GW170817 and really bring multi-messenger astronomy, this astronomy made of multiple messengers such as light, neutrinos, and gravitational waves into its full bloom and its full potential.